In this video, we're going to talk about limit points and convergent sequences and their relationships to open and closed sets. So first we'll give the definition. Let XD be a metric space and let A be a subset of X. A point X in X, or an element of X, is a limit point of the set A if every open set containing the point X contains some element A in A such that X is not equal to A. So suppose that A is that squiggly set we see over there. This one happens not to be connected. So it's saying that a point X is a limit point of A if every open set U containing X also contains some other element A that is in the set A where A is not equal to X. So our picture might look like that. We have this open set around the point X. Little a is an element of big A that is in this open set U, or it might be the case that our element little x that is a limit point of A might not actually be inside of A, it might be just outside of it or outside of it in some way, but it's still the case that every open set U containing X also contains some element A not equal to X that is in the set A. So that's the definition of a limit point. So let's look at an example. Say that we're in the real numbers with the usual metric on R. So we're on the real numbers usual metric. In other words, the distance between 2 points X and Y is equal to the absolute value of X minus Y. What are the limit points of this set 0, 1? This is the open interval from 0 to 1. So I'd like you to pause and think about this with this definition. First, we're going to show that every point in this open interval is a limit point in this particular set. So let's let X be an element of this open interval from 0 to 1. So maybe X is here. And we'll let U be an open set containing X. So U is some open set containing X. Could be anywhere. So it's on this real line somewhere. Maybe it's a subset of 0, 1, and maybe it's not. But here's our set U, say. And so what we want to show is that there's some other point A, such that A is an element of U, and A is an element of this particular set that we're trying to find limit points of. So to do that, what we can do is notice that from our previous theorem, and it's part B of our previous theorem, that tells us that since U is an open set containing the point X, that means there's some epsilon greater than 0 such that the ball centered at X of radius epsilon is contained in the set U. This is a really useful theorem that we'll use over and over, that if a set is open, then this must be true about it for any point in the set. So what we're saying now is that there's some ball of radius epsilon that is, so this would be X plus epsilon, X minus epsilon, contained in the set U. Now, do we know that there's some point A that is inside of there? Sure, we could do, let's let A be the point X plus epsilon over 2. The ball centered at X of radius epsilon is all things of distance less than epsilon from X. Epsilon over 2 is the distance here. So this would be an element of this ball. And that tells us that it's also contained in U. And A is not equal to X. So this tells us that, for any arbitrary open set, there is some other element other than X itself that is contained in this set that we're trying to find the limit points of. And therefore, X is a limit point of the set 0, 1. Similarly, we can also show, it's also the case that 0 and 1 are limit points of the set 0, 1. If we were thinking about 0, then the exact same proof would also work. If we wanted to show that 1 was a limit point, we just need to look at x minus epsilon over 2. So let's say that let U be an open set containing the point 1. Then the ball centered at 1 with radius epsilon must be contained in U by definition, or by this theorem about open sets. And this tells us that the point 1 minus epsilon over 2 would be an element of this ball centered at 1 of radius epsilon, which is a subset of U. And we know that 1 minus epsilon over 2 is not equal to 1. So this tells us that 1 is a limit point. So we've shown that everything inside the closed interval from 0, 1 is a limit point of the open interval from 0 to 1. So what if we take something outside of that interval? Let's say that we take, some x that's just outside of it. So let's let x be greater than 1. Then x must be equal to 1 plus delta for some delta greater than 0. So can we think of some open interval that contains x that does not intersect with U, that has no points inside of U? Sure, we definitely can. So let's think about the ball centered at x with radius delta over 2. So note that the ball centered at x with radius delta over 2 is an open set containing x that has no intersection such that there is no A in the intersection of this ball and the set 0, 1. And this tells us that, therefore, this x, which is greater than 1, is not a limit point of the set 0, 1. And you could do the same kind of proof for some x less than 0. So similarly, x less than 0 will not be a limit point. So the set of all limit points here, so the set of limit points of the set 0, 1 open is the set 0, 1 closed in this particular case. Here's a theorem about limit points in a set. So let xd be a metric space and let A be a subset of x. A point x in A is a limit point of A if and only if the distance between the point x and the set A without x is equal to 0. Just as a reminder, if we talk about the distance between a point and a set, then that's equal to the greatest lower bound of the distances between that point and elements of that set. So the set in this case is the set A other than the point x itself. Okay, so we're trying to show that x is a limit point if and only if that greatest lower bound of the distances between the point and the set without that point is equal to 0. Let's first prove this forward direction. Since it's an if and only if, we have to prove both implications hold. So let's suppose that x is a limit point of A, and we're going to do this proof by contradiction. So suppose for contradiction that the then is false. In other words, that the distance between x and A minus x is not equal to 0. The distance can be 0 is the smallest it can be, so if it's not 0, it's got to be greater than 0. Let's call it epsilon, which is greater than 0. Okay, now let's consider the ball centered at x of radius epsilon, which is an open set. So you proved in previous homework that the ball centered at x of radius epsilon is always going to be an open set in any set. So by definition of limit point then, because this is an open set, there must be some A other than X, such that A is in the big set A and A is in this open set. So let's just write that down. By definition of limit point, because X is a limit point, there exists some A not equal to X, such that A is in both the ball centered at X of radius epsilon and in the set A. Now, here is an issue. What we see then is that then A is an element of A, and the distance between X and A is less than epsilon. And this contradicts that the distance between X and A minus X was equal to epsilon. And so we have a contradiction. Because we have this contradiction, we suppose the if statement, we supposed for contradiction the negation of the then statement. We found that that could not possibly be true, therefore the if-then statement holds. Now to show the reverse implication, let's suppose that it is true that the distance between X and the set A minus X is equal to 0. We want to show that X is a limit point for the set A. So to show that, we can let U be an arbitrary open set, be an open set containing X. So U is an open set containing X. So let's just draw the picture we've got so far. We've got our set A, we've got our larger set X, we've got some set A inside of that, and we've got some point X where the distance between X and A minus X is 0. And now we've got some open set U, some arbitrary open set U, and what we want to show is that there exists some A not equal to X, such that A is an element both of the open set U and of the set A. So that is our goal. Now, let's suppose again for contradiction. Suppose for contradiction that this is not the case. Suppose there is no element A in A, such that A is not equal to X and A is in this set U. What would happen in that case? Then by, again, our previous theorem, so by our previous theorem, that part B of that previous theorem, since U is open, that means that there is some epsilon greater than 0, such that the ball centered at X of radius epsilon is contained inside the set U. Since then, there is no A in A, such that A is an element of U. That tells us that the distance between the point X and the element A must be greater than or equal to epsilon. Because A is not in here, it's not of distance less than epsilon. So it's got to be of distance greater than or equal to epsilon for every A in the set A. And now this contradicts that the distance between X and A minus the point X is equal to 0.